Hello and welcome everyone. So this is our session on fluid mechanics, particularly on problems, exercises on fluid pressures, which involves manometers. Yours truly, I'm Engineer Ronjan R. Garmi. Just sit back, relax, and listen carefully to the concepts. As for our learning objectives, at the end of this session, students will be able to: Number 1. Apply basic concepts on fluid physical properties to problems on pressure. Then solve problems on fluid pressure, and also relate with the units of measurement on pressure. So let us talk about the pressure basics before we are going to have examples. So we say that the pressure is just equal to the unit weight times the vertical height h. So this is a gauge pressure, wherein gamma h going downwards, that will be denoted by positive sign, and then going upward we have negative sign. We applied the principle: same level, same liquid has the same value of pressure. We also recall that gamma is equal to the specific gravity times the unit weight of the standard substance for fluid, which is water. In gauge pressure, pressure is zero at liquid exposed to atmosphere. In absolute pressure, pressure is equal to atmospheric pressure at liquid exposed to atmosphere. We can express the relationship of absolute pressure to that of the atmospheric pressure and the gauge pressure. The absolute pressure just simply involves the atmospheric pressure plus or minus gauge pressure. The atmospheric pressure has a value of 101.325 kilopascal, equivalent to 14.7 pounds per square inch, which is also equal to 760 millimeter of mercury. So let us now go on particular examples. So in this example, first we determine the gauge pressure at a point in a body of oil. So this body of oil has a specific gravity of 0.8. So this point is 2.5 meter below the surface. If the atmospheric pressure on the free surface is 101 kilopascal, what is the corresponding absolute pressure at that point? So we can illustrate this by simply having our liquid surface of oil with S of 0.8. We denote a point below this surface, which is 2.5 meters head or vertical height from the surface. So our unknown here is the absolute pressure at this point. So as a matter of solution, we simply write first our gauge pressure equation, which is equal to gamma h. So gamma can be expanded to specific gravity times gamma of the standard substance water. So with that, we can simply substitute the value of the specific gravity and that of the value of the gamma of water with the value of the vertical height 2.5. So remember that the units are consistent in a way that we use kilonewton per cubic meter and meter for the gamma and the height respectively. So therefore, we come up with the value of 19.62 kilonewton per square meter or kilopascals. So this is now our computed gauge pressure. So moving on to the absolute pressure, we just simply add the atmospheric pressure. And from the given, we have 101 for the atmospheric pressure plus gauge pressure just computed. So with the sum, we have 120.62 kilopascal for the absolute pressure. So this is about this problem. Next, a pressure of 150 kilopascal is equivalent to how many meters of water and of how many meters of mercury with specific gravity of 13.6. And in absolute units, what are the corresponding pressure head assuming standard conditions? Again, we start our solution with the liquid surface of water and the point below that the head of water, and that head of water is yet to be determined. Given the gauge pressure 150 kilopascal, we can derive the head of water by its formula that the pressure is equal to gamma H. So start with this. For water, we write the formula P is equal to gamma H. This is for water. Now we substitute the value of the required pressure, 150. So that equates to the specific gravity times gamma of water times the head of water. So we substitute the other given. Remember that the specific gravity of water is equal to 1. Now we can derive the value of the head of water. So that equates to 15.29 meters. So knowing that, we can have the mercury surface, liquid surface. So this mercury has S of 13.6. Of course, the head will now be different from that of water, but we have an equivalent gauge pressure, and that is what we need to satisfy. We need to satisfy an equivalent height of water to that of mercury to attain a pressure of 150 kilopascals. So what would be that height of mercury? So for mercury, again, we write the equation gamma H, this time for mercury. We substitute the value of the required pressure, 150, and equate it to the specific gravity of that mercury times gamma of water times the head of the mercury. Substituting the given of S and gamma of water together with the pressure, we can now compute for the head of the mercury. So the head of the mercury is equal to 1.12 meters. Notice that there is a substantial decrease of the height comparing to the water. That is because your mercury is having a greater value than that of the water in terms of gamma, or the unit weight. So in absolute units, knowing the head of water in terms of gauge pressure, we can derive that in terms of absolute units, the height. So we start with the equation that the absolute pressure is equal to the atmospheric pressure plus gamma h. So with that, we can substitute gamma h absolute for pressure absolute, and we maintain atmospheric pressure, and gamma h, and add on gamma h of water. So we substitute the values 9.81 times head in absolute, that will be equal to 101.325. So this is the value of the atmospheric pressure under standard conditions. So that would add to 9.81 times the derived height a while ago, 15.29. With that, we can now derive the equivalent head in absolute units of the 15.29 head of water. So that will equate to 25.62 meters. For mercury, we do the same. We write the equation that absolute pressure is equal to atmospheric pressure plus gamma h. And again, expand the equation. Gamma h for absolute is equal to atmospheric pressure plus gamma h of that mercury. So we substitute the gamma for mercury, 13.6 times 9.81 times h absolute is equal to 101.325 plus 13.6 times 9.81 times the derived head of mercury a while ago, that is 1.12 meters. Hence, we can get the equivalent head in absolute units, that is equal to 1.88 meters. So proceeding to another problem. Oil with S is equal to 0.8 is 0.91 meter deep in an open tank which is otherwise filled with water. If the tank is 3.05 meter deep, what is the pressure at the bottom of the tank? So we start with illustrating the problem. We draw a tank. This is an open top, wherein this is filled with oil. So remember that comparing oil with that of water, water is heavier than that of the oil because oil has only 0.8 specific gravity compared to that of one of the water. So naturally, with that premises, oil will just float on top of water. The lighter the liquid is, that will float on the heavier liquid. So therefore, oil will be on top of water. So water is below oil, and oil has a given height of 0.91 meters. Given the total height of 3.05 meters, of course, we'll just have to get the difference of 3.05 minus 0.91 meters, and that will be the height of water below the oil, that is 2.15 meters. So we denote a point here, say that is P1, and P1 is the unknown in the problem. P1 is the pressure at the bottom of the tank. So we now proceed to our solution, wherein we just apply summation of pressures is equal to end pressure. We can start on top or we can start at the bottom. In this case, I'm going to write my equation starting at the bottom. And then from that, we say we start with P1 and then we go up. Therefore, we denote it by negative gamma h of water. And then we further go up negative gamma H of oil. And the end pressure is the oil surface that is exposed to the atmosphere. So remember that if any liquid is exposed to the atmosphere, the pressure there is 0 when considering gauge pressure. And then from that, we can expand our equation by substituting the given heights and the given specific gravity. Then we can now derive the pressure at the bottom equivalent to 28.15 kilopascal. So this will be the answer to this problem. So moving on to another problem. A large square tank has a 200 mm nozzle 5 meter below the water level. What is the pressure at a point 3 meter below the water level? Again, we illustrate the problem by having a water surface, and below that water surface 5 meters we have a nozzle. The question is, what is the pressure at point 3 meters below the water level? So this is denoted by PA. Remember that the opening at the bottom or 5 meters below the water level has no bearing to that of the pressure 3 meters below the water surface, which is the unknown. So again, we apply that summation pressures is equal to end pressure. This time, I'm going to start writing my equation on top. So on top, we have an exposed liquid surface, so that will start with 0, and then we go down to the point 3 meters below the water, so plus gamma H of water. That would equate to the end pressure, which is equal to PA. Now substituting the value of the height and the gamma of water, we can derive now the pressure 3 meters below the water surface. That is equivalent to 29.43 kilopascal. So that will be the answer to this problem. So moving on to another example. If a water with the height of 1.2 meter in a manometer is replaced by oil with a specific gravity of 0.75, what is the equivalent height? So in this case, we have a manometer that is filled with water, and the height of water according to the problem that is 1.2 meters will have a corresponding pressure, say PA. So we replace water by oil 0.75. Okay, we do not know this yet, the height of oil, but we need to satisfy the same pressure generated by the head of water that is equivalent to 1.2 meters. So for our solution, we'll just have to equate that PA due to water will be equal to the pressure at A due to oil. So pressure equation starting on top, 0 plus gamma H of water for the left hand side of the equation, and for the right hand side we deal with oil, 0 plus gamma H of oil. We substitute the values and we have a variable unknown, H of oil. So solving now for the head of oil, the equivalent height would be equal to 1.6 meters. Notice that the head of oil is greater than the head of water. Why? Because oil is lighter than water. So therefore, it would need to have more height compared to that water to satisfy an equivalent pressure to that of the water. So another problem here we have with the normal barometric pressure at sea level, the absolute pressure at an elevation of 1215.5 in terms of height of mercury is equal to blank. We have here the given weight of air equivalent to 11 Newton per cubic meter, and Hg is equal to 760 millimeters of air at sea level. So we start with the sea level surface. Of course, that would be elevated a certain point, say on top of a mountain. We take the height 1215.5 from the problem. So this shall generate a certain pressure at A at this point. So first, in terms of the height of the mercury, there will be also an equivalent pressure at A given a height of mercury in absolute units. So this is actually the unknown in the problem. So as a solution, we write PA is equal to gamma H initially for the gauge pressure. So we consider the weight of air, that is 11 times the given height 1215.5. Hence, therefore, the pressure at A given this height with the weight of air, that will be equal to 13.3705 kilopascals. So in terms of mercury, the pressure at A is equal to gamma H of mercury. Of course, we just utilize the equivalent PA, what we have acquired from the gas or air, that is 11 Newton per cubic meter. So therefore, the PA computed is 13.3705 will be equated to gamma H of mercury. Substituting the specific gravity, we can get the value of height in terms of mercury, that is 0.1 meter or equivalent to 100 millimeter. So remember that absolute pressure is equal to atmospheric pressure plus or minus gauge pressure. So in this case, we have negative since we are going upwards from that of the sea level. And then all of this will be divided by the gamma. Hence, the absolute pressure will be divided by the gamma as well as the atmospheric pressure, and the gamma H will be divided by gamma. Hence, that would be cancelled. Remember that P over gamma refers to the pressure head. So P absolute over gamma, that is the pressure head in absolute units, and then atmospheric pressure over gamma, that is pressure head in terms of atmospheric value, and then H here is the vertical height. So all in terms of mercury. Therefore, the height absolute in terms of mercury, remember that the atmospheric pressure is equal to 101.325. Dividing that by 9.81 and 13.6, we can have 760 millimeters. Remember that the value of the pressure is equal to 101.325 also equal to 760 millimeter of mercury. Again, to derive that, just divide 101.325 to that of the product of 9.81 times 13.6. We can arrive with 760 or 0.76 meters, or that is 760 millimeters of mercury. So we now subtract what we have derived on the gauge pressure, that is negative 100. So therefore, the absolute head of the pressure above 1215.5 meters is equal to 660 millimeters of mercury. So moving on to another problem. We have a pressure gauge at elevation 6 meter at the side of a tank containing a liquid reads 90 kilopascal. Another gauge at elevation 4 meters reads 110 kilopascal. Compute for the specific weight. Of course, we'll be having here a tank in terms of a conduit wherein there will be a liquid in it with the unknown gamma. Of course, at elevation 6 meters and 4 meters, there will be given readings of pressure. So, take note that with those elevation, we can derive the difference between those elevation. That will be equal to 2 meters. So at elevation 6 meters, we have a reading of 90 kilopascal. And at elevation 4 meters, we will be having a reading of 110 kilopascal. We denote this as P1 and that other one is P2. Then proceed with the solution. Again, we apply summation pressures is equal to the end pressure. Writing the equation starting on top, we have P2. We are going down towards P1, so that is plus gamma H is equal to P1. We substitute the values, so the reading of P1 is 90, or I say P2 is 90, and then plus unknown gamma times the head of 2. That will be equal to the end pressure with the reading of P1 equal to 110 kilopascals. So therefore, we can derive the gamma is equal to 10 kilonewton per cubic meter. So that would be the answer on this problem. So moving on to another problem. Calculate the pressures in kilopascals at points A, B, C, and D. Assume unit weight of water equivalent to 9.79 kilonewton per cubic meter. So here is a tank with several divisions. And this is designated as point A. That is point B. That is point C. And that is point D. We have the following dimensions or vertical height of various liquids. So actually, there will be two liquids here, water and oil. And the confined portion will be air. For our solution, if this is point O, we start writing the pressure equation from O to point A. So we apply summation pressures is equal to end pressure. And then of course, we are towards A now. We apply same liquid, same pressure. Because as we go down, that is positive gamma H, we go up still with the same level and the same gamma. So it will just cancel out. Therefore, we are on this level. And from that level, we can proceed writing the equation towards A. So 0, we are now going upwards, minus gamma H of water, that would equate to the end pressure, that is PA. Substituting the value of gamma, remember that gamma here is specified in the problem. So we consider 9.79 for gamma of water times the height of 0.8. So that would be the sum of 0.4 and 0.4. So therefore, we can now get the pressure at A equivalent to negative 7.832 kilopascal. So negative means that the confined air at point A is under suction. For the next step, we now write our pressure equation from 0 to B. So we go down from the open exposed surface up to B, going downwards. So we start with the exposed portion, that is 0, plus gamma H of water, and the end pressure will be equal to pressure at B. We substitute the value of gamma, 9.79, and the height involved here from O to B is 0.5. And then from that, we can derive pressure at B equivalent to 4.895 kilopascal. Again, apply same liquid, same pressure. We are now going downwards and going upwards. That will just cancel. So at that level, pressure B will be utilized. Now we approach B to C. So from that surface, we now proceed to C. And remember that gamma of air compared to that of any liquid is very negligible. So therefore, if we add gamma H of that air, that would have a very slight effect or negligible effect on the values. Hence, we can say that the pressure at B is equal to pressure at C. Now we are now on the level of C. So to solve for pressure at D, we write the equation from C to D. So we will now go downwards from C. So therefore, the pressure at C plus gamma H, and the involved liquid here is oil, that would be equal to the end pressure, which is equal to pressure at D. Substituting the value of PC, 4.895, and the values of the height and the specific gravity. The height here, in the figure, we can have the sum of 1 plus 0.5 plus 0.4. So that will be equal to 1.9. So we can now derive the value of the pressure at D, which will be equal to 21.64 kilopascals. So that is about this problem. Next problem. Piston A has a cross-section of 1,200 square centimeter, while that of B is 800 square centimeter. B is higher than A by 2 meters. If the intervening passages are filled with oil having a specific gravity of 0.8 and the force of 4 kilonewton is acting on B, what must be the pressure and the force exerted at A? So here's the setup of the two pistons. We have the given cross-section that is dipped into the piston through the oil. The oil is the intervening fluid on this hydraulic system. So solution, of course, we wanted to convert our units. So from centimeter, we can convert that into meters by the conversion factor that 1 meter is equal to 100 centimeter. So all of those will be squared since we are converting as square centimeters. So from that, we can have our area of piston A equivalent to 0.12 square meters. Similarly, the area of piston B is 800 centimeters squared. Using the same conversion factor, we can arrive with an area of piston B equal to 0.08 square meter. Now that all our area is in terms of meter, we will now have a consistent unit to be paired with the force of 4 kilonewton. So the force of 4 kilonewton is within at B. So our solution will be dictated by the given, of course, starting from that given force of B equal to 4 kilonewton. Recall that the pressure is just equal to the force all over area. So for B, the pressure at B is equal to the given 4 kilonewton divided by the area 0.08. So remember that the force is in terms of kilonewton and the area is 0.08 in terms of square meter. Kilonewton per square meter is in kilopascal. So therefore, the pressure at B is 50 kilopascals. Now from that, we can now write the pressure equation from B to A, or if you want, from A to B. So in this case, I'm gonna write my equation from B to A. So starting at B, we have PB plus gamma H of oil is equal to PA. So the computed pressure at B is 50. We substitute the value of specific gravity and height of oil, that is 2 meters, towards the end pressure of PA. Remember, from B, we will go down. So therefore, our sign here is positive or plus. So from that, we can now derive the pressure at A, which is equal to 65.77 kilopascal. Again, we can connect pressure to the force by the formula. The pressure is equal to force all over the area. So substituting the values, pressure at A is 65.77. The area of A, the piston at A, is 0.12 square meters. Hence, we can get the value of the force equivalent to 7.88 kilonewton at point A. So that is about this problem. So next we have the hydraulic jack shown is filled with oil at 55 pounds per cubic feet. Neglecting the weight of two pistons, what force F on the handle is required to support the 2,200 pound weight? So here's the setup of the hydraulic jack. there will be a handle that is hinged to the plate, and then of course there will be a platform connected to a piston to support the 2,200 pounds. So the dimensions are given on the handle and the connection of the pin and to that of the smaller piston. So our requirement here is what will be the force to lift the 2,200 pounds. So the intervening liquid here is oil of specific weight of 50 pound PCF. So this piston is 3 inches in diameter, and that piston is smaller one that is 1 inch in diameter. So if this will be labeled as point A and the other piston will be point B, we now proceed to the solution. Again, we write the connection formula of the pressure to that of the force. The pressure is equal to force all over area. For A, we can substitute the value of 2,200 pounds. Again, we are dictated by the given. So therefore, we have started with the given 2,200 pounds, and that involved the piston at A. Hence, the piston has a circular cross-sectional area. We can express the cross-sectional area of a circle with pi over 4 times d squared. Substituting the value, we'll arrive with the pressure at A equivalent to 311.24 psi. So here, we do not need to write a pressure equation, knowing that points A and B are at the same level. So same level with the same liquid, the pressure will be equal. Hence, we can say that PA is equal to PB, equivalent to 311.24 psi. So we write the equation for B, pressure equation in terms of force. So pressure is equal to force all over area. For B, the given for the formula is the pressure, and the area of B can be expressed with the cross-sectional area of 1 inch diameter, expressed by pi over 4 times 1 squared. So here, we can derive the force at B. So the force at B will be transmitted considering the free body diagram of the handle. So on the handle, we have here force F and force B. On the pin connection, remember, on the pin connection, applying our knowledge in mechanics, engineering mechanics, there will be two forces there, that is horizontal and vertical. Nevertheless, we'll just have to consider that point as O. By taking moments at O, we can neglect the moment arm of the said forces. Having these two have a 1 inch distance and 16 inch distance from F to the pin, we can utilize those distances in taking moments. So FB will have a counterclockwise direction. So therefore, that will be denoted by negative sign. Negative 244.44 times the moment arm of 1. While that of the force F from O will have a clockwise direction. So therefore, plus F times 17. So that will be equal to 0. And therefore, the required force will be derived. F is equal to 14.38 pounds. So that is about this problem. We now go to examples on manometers. So in this problem, we are going to compute the pressure at the center of conduit M. We have here water and mercury of specific gravity 13.6. So the levels or the head are given for these various liquids. Solution. We start with this open liquid, that is 0. And then we go down. The involved liquid is gamma H of mercury. So 9.81 times specific gravity 13.6 times the height in terms of meter, that is 35 over 100 or 0.35. We go down and we go up. Hence, we apply same level with same liquid. So gamma H of going downward and gamma H of going upward will just cancel in your equation. So we are on this level now. We further go up towards M, the level of M, and the involved liquid now will be water. So that is 9.81 times S of water, 1, times the head of water, 0.5. And that would equate to the end pressure, PM. And PM could be readily computed equivalent to 41.8 kilopascals. So moving on to the next example. Determine the gauge and absolute pressure at point M. So in here, the manometer is dipped into an open tank. So the given head is given 10 centimeter and the involved liquid here is again mercury 13.6. So our task is the pressure point M, given that this is an air having a gamma of 12 Newton per cubic meter. So for our solution, we'll just have to write our pressure equation starting at this open liquid. Actually, you may opt also to start with point M, but this time I'm going to start with the open exposed liquid surface. So that will be 0. And then we go up. That is negative gamma H. The gamma is 9.81 times 13.6. The head is 10 over 100. Again, we go up. And that will just cancel going down. Same level, same fluid. We are now on this level. We further go down towards the level of point M. So therefore, we add gamma H of air. So gamma of air is 12 over 1000 times Z. So please don't bother about Z because that will be negligible. So we can now equate our equation with the end pressure M. Solving for M, you'll be having 13.34 kilopascal denoted by negative sign, meaning that the pressure at the conduit is under vacuum or suction. So this is on the gauge pressure. For absolute, again, we apply this formula. Absolute pressure is equal to atmospheric pressure plus or minus gauge pressure. Absolute pressure, we consider the atmospheric pressure under standard conditions, that is 101.325. So the operation involved here is negative. So 101.325 minus 13.34, that will be equal to PM is equal to 87.96 kilopascal. So notice that your absolute pressure at M is less than 101.325, and that is an indication of the pressure being under suction, and that will be absolute pressure. Moving on to another problem. Determine the pressure difference between points M and N. So in this case, this is a manometer wherein there will be no open end for the manometer. On our first two examples on manometer, we have an open manometer wherein we can compute directly for the pressure, but this time we cannot derive the particular pressure at M and N, but this is more on the difference of pressure between M and N. Again, that is because there is no open surface here. That is why this manometer is called differential manometer. It measures the difference between two elevations. So in here we have the involved liquid is water for both M and N sides, and otherwise filled with oil with S of 0.85. So as a solution, we start writing our equation at conduit M, that is BM. Then we go up gamma H, and our H here, or the head, is Y. So we go up, that is denoted by negative. The involved liquid here is water, so 9.81 times 1. We further go up. Now this time the involved liquid is oil of S.85. We consider that S in the equation as well as the height in terms of meters. We are now on this level. Again, we apply same level, same fluid. Going up and going down will just cancel that expression. So therefore, we can proceed to moving downwards further at the level of N, and the involved liquid at that side is water, having a head of X. We can now equate to end pressure Pn. So we can transpose Pn on the left hand side of the equation. That would become negative. So therefore, we have expressed the unknown, which is Pm minus Pn. So we equate it to the expressions, and of course, notice that 9.81 is common to the remaining terms. Transposing all of the terms on the right side and factoring out 9.81 will come up with y minus x plus 0.408. So 0.408 is the product of 0.85 times 0.48. Notice here in our equation that there will be two unknown variables further added in the equation. So don't worry about that. We can deal with that by geometry. Considering that this level are equal on left portion and the right portion. So therefore, x plus 1.7, by the way, 170 is 1.7 meter, or 170 centimeter divided by 100, that will equate to 1.7 meters. So 1.7 plus x on the right portion will be equal to the left portion. Here, 0.48 plus y. And then from that condition, we can derive y minus x equal to 1.22. Okay, moving back to our equation here, we'll just substitute 1.22 on y minus x. Therefore, we can now get the difference in pressure between conduit M and conduit N. Pm minus Pn is equal to 15.97 kilopascals. So moving on to another problem, we have a U-tube shown is 10 mm in diameter and contains mercury. If 12 ml of water is poured into the right hand leg, what are the ultimate heights of two legs? Assume unit weight of water is equivalent to 9.79 kN per cubic meter. As a general rule, when we have the same liquid involved in a pipe, always that the liquid surface on both ends will have the same level. So in this case, the filled U-tube with the mercury is having a head of 120 millimeters. Now we are going to fill this right hand leg with 12 ml of water. So what happens now is this will now be the 12 ml of water that will tend to push your mercury on that direction. So therefore, y here will become a variable, and the left hand side of the tube will be equal to 240 minus y. Why 240 minus y? Because as you can see here on the upper figure, that if your mercury will be fully pushed on the left side, that 120 will just be doubled. Okay, so 120 plus 120, that is 240. So because there will be a variable y there, that 240 will be that y will be deducted to 240. So therefore, that is 240 minus y. Okay, so x here will be determined yet. So actually that will be a part of our solution. We solve for x in millimeters by the given volume. So before we can deal with the volume, of course, we need to convert that into meters. So the connection is ml muna to that of liters, and then from liters to cubic meter. So 1000 milliliters is equal to 1 liter, so that we can cancel ml. And 1000 liters will be equal to 1 cubic meter, so that we can cancel liters. Now, 1 meter is equal to 1000 mm. Since that is cube, the volume is in terms of cube, therefore we cube all of the terms here so that we can cancel that one and arrive with cubic millimeter in units. So that will be equal to 12,000 cubic millimeters. We are now dealing with the tube, so therefore the volume is just equal to the base area times the height. And the base is cylindrical. Cylindrical volume actually has a circular base. So the area is pi over 4 times d squared. So the height here will be x variable. We just substitute the diameter of the U-tube, that is 10 squared, 10 raised to 2. Having that, we can derive for x. So x will be equal to 152.79 millimeters. We can now start writing the equation starting from the left. Starting from the left, the exposed portion will be 0, and then we go down 9.79 times 13.6 times 240 minus y. And then we go up with mercury also. So that will be denoted by negative 9.79 times 13.6 times the head of y. And then again we go up negative 9.79. This time this is water, so we multiply that by 1 multiplied by the head, 152.79. And the end pressure is equal to 0 since the water surface is exposed to the atmosphere. So take note that all of this will be divided by 1000 because the head in the equation is in terms of millimeters, so we need to convert that into meters. Solving now for y, we'll have 114.36 millimeters. Knowing y, we can now derive the right column height, that is x plus y, or 152.79 plus 114.36. So that would sum to 267.2 millimeters. Likewise, we can solve for the left column height, that is 240 minus y. 240 minus 114.36. That will be equal to 125.64 millimeters. So those are the ultimate heights that are unknown in the problem. So moving on to the next problem. A cylindrical tank contains water at a height of 55 mm as shown. Inside is a smaller open cylindrical tank containing cleaning fluid with specific gravity of 0.8 at height h. If pressure B reads 13.4 kilopascal and pressure C is equal to 13.42 kilopascal, what are the gauge pressure PA and the height of the cleaning fluid? Assume that the cleaning fluid is prevented from moving to the top of the tank. So for our solution, we write the pressure equation from the given, utilizing the given, of course. So from PA to PC. So question here, why not directly go to PA to PB? Because PA here is unknown and H is also unknown. So therefore, we cannot go directly with the solution writing from PA to PB directly. So we need to start our solution from PA to PC to derive the value of PA. Now, PA will be needed to the solution of having PA approaching PB. So, nevertheless, we proceed now with the solution. So, we write PA plus gamma H of water. That will be equal to PC. We substitute the value of the head of water, 0.055, or that is 55 over 1000, to make it in meters. And PC is equal to 13.42. Okay. So therefore, PA will be equal to 12.88 kilopascal. So knowing PA, we can now proceed with PA approaching PB. So PA, okay, plus gamma H of water, and then plus gamma H of kerosene. Eventually, we have the end pressure, 13.4 kilopascal for PB. PA here is computed to be 12.88 plus 9.81 times 55 minus H. So this will be divided by 1000, again, to be consistent that our units is in meter. So we add on the kerosene portion, we have 9.81 times 0.8 times H. Again, this will be divided by 1000 to convert millimeter to meter. So that will be equated to your end pressure, PB, is equal to 13.4. Manipulation of equation will have H equal to 0.1 meters, which is equal to 10 millimeters. So I think that ends our session. Have a good day, class, and it is suggested that you practice problems. Thank you and have a good day.